Grade 12 Physics, Dynamics, Note number 8, Non-Inertial Frames of Reference. So in this note, we're going to take a look at a non-inertial frame of reference, so something that's accelerating, and we're going to use something on the accelerating object to try and determine the value of its acceleration. So first of all, let's examine a ball on a bus. So let's say you're sitting on a bus that's either at rest or constant velocity, and there's a ball on the floor of the bus beside your feet. So at rest or constant velocity, we know that the ball should stay at rest or constant velocity, but it would stay at rest relative to you. But now let's say the bus accelerates. If it accelerates in the forward direction, what are you going to see the ball do? The ball is going to roll back. How about when the bus accelerates backwards, so when it's slowing down? The ball will roll forward. Now let's say the bus accelerates to the left, which means it's turning towards the left. We're going to see the ball roll right. And then finally, the bus turns right, the ball is going to roll left. The ball is going to basically do anything opposite to what the bus does. But what's actually happening? Why is the ball rolling when the bus accelerates? So if in the reference frame of someone on the ground, if we take a look at that, what is the ball doing with respect to them? In fact, to them, the ball doesn't move at all. If the bus accelerates, the ball just keeps on doing what it's doing because of its own inertia. If it's heading in a straight line, it wants to keep heading in a straight line. If the bus accelerates around it, it's going to make it look like it moves to someone on the bus, but not to someone on the ground. So in the reference frame of someone on the bus, we'll get all the results above. So now let's use a numerical example, but instead of looking at a ball rolling around on a bus, we're going to take a look at some dice swinging from a rearview mirror. We know that if a car or a bus accelerates, the dice will swing forward or back according to what it's doing. So here in this example, let's say we're on a spaceship, and the spaceship is decelerating, so it has negative acceleration. There's a dice hanging from a rear view mirror, and the dice are going to make a 12.5 degree angle. From that, we're going to try and calculate the deceleration, or the negative acceleration. So let's draw a picture with the motion of the spaceship in that direction. So the dice are going to swing forward, right, in the direction of motion to signify the slowing down. There's the 12.5 degree angle. So again, deceleration is going to occur in the x direction. So let's draw a free body diagram of the dice. Gravity is going to be straight down. Tension is going to be up along the chord. Now we know that the deceleration is along an x-axis. We can't break Fg down into any component along that f-axis. So we're going to have to break down tension. Tension in the x and tension in the y. We notice though tension in the y is going to be equal to Fg. Now looking at the x direction, F equals ma. So in the x direction the only force is Tx. But what is Tx? We have to figure out how it's related to anything else. Tx, we can relate it to Ty through tan. Tan of an angle is opposite over adjacent. So tan of an angle is Tx over Ty. So here Tx is going to be Ty tan theta. So we can sub that in for Tx. Now why that's handy is because Ty we know is equal to Fg, which is mg. We can sub that in, and we notice here there's an m on each side, they're going to cancel. So the acceleration of the dice is going to be g times tan theta. So here 9.8 times tan of whatever angle it is, 12.5 degrees. Acceleration is going to be negative 2.17 meters per second squared.